Yes. Very good. See how, okay, they're on the right side, they are. Okay. Right.
Well, it's 3 minutes past, half past. So before I forget, both Maxi and Raoul told me to remind people that there will be coffee afterwards. Hopefully. So at least it has been ordered. And there will also be biscuits if things work. Right? Okay. And the second thing, for those who are online, this session is being recorded. So if you don't want to be seen in the video, then you have to switch off your cameras. So it's my pleasure to introduce Rainer Hexelmann for the colloquium today. So he has a long and distinguished career, which I'll briefly summarize. So Rainer studied philosophy, sociology, and political sciences in Bochum in Germany, and got his PhD from the University of Essen, and then the habilitation at Karlsruhe in Germany. From 1986 to 89, he was a Heisenberg Scholar of the German Science Foundation. That's a very distinguished award. And then became a full professor in Bremen in 1988. And then in 1996, he took up a chair at Bayreuth University. And there, among many other things, he designed a degree program on philosophy and economics. And since 2010, in parallel, he was the director of the Bayreuth Center for Modeling and Simulation of Socioeconomic Phenomena, which I guess resonates with many of us here at IFISC. And he's now retired from Bayreuth, but is continuing to work and is doing teaching and research as a professor at the Frankfurt School of Finance and Management. And I stress it's teaching and research. So he's still very much actively involved. And the topic for today is bounded confidence, a deceptively simple model. So welcome, Rainer. Thank you for coming here. And we look forward to your talk.
Thank you very much. It is not. Oh, I think I know the mistake. It will become loud for a moment. Yes, repaired. Okay. Many thanks for the invitation. Many thanks for the occasion to present something about the bounded confidence model, a model that, to my mind, and I learned it the hard way, by the way, is deceptively simple, and it deceived its inventors as well. So the alternative title to this one could also be Bounded Confidence Revisited, what we overlooked, underestimated, and got wrong. We published, Ulrich Krause and me, we published together, frankly stating, Ulrich Krause invented the model. Both we were in Bremen at the university. Together, we did long distance running. And during long distance running in, I think, when was it? Probably 87, 89, or this time. He came up with the model, but he couldn't cope with the model because he was a traditional mathematician. He does it with paper and pencil. Here, a lot of calculations involved. He couldn't do that. And since he tortured me during long distance running with questions about the model, I finally said, I will program that and we will find out. That was the history of the invention, and we published a very successful article in 2002. And now I come back to that article because we got lots of things wrong, and we can explain why. And I will go into the details now. First, to get a feeling about the model, it is extremely simple. Assume a group of, let's say, experts on something where probabilities are involved. All experts have a certain opinion. Nobody is totally sure. Everybody is willing to revise in light of views of others that he or she considers as a competent others. They revise their opinions and so on and so on. What will be the outcome? Think of, for the beginning, later I come up with other interpretations, Delphi study format. That might be an example. That is intuitive. We need a bit more clarification, and that is very easy. We have a set of individuals. We have a discrete time, and we start with opinions from the unit interval. That are the start opinions, and now the simple idea made precise. For an updating of the opinions, everybody takes the opinions of others which are not too far away, meaning that the distance between I is our focus agent, and the other ones, J, is not greater than epsilon, the confidence level, or the confidence interval that is defined by that. And then we have a set of the ones that are inside of I's confidence interval. That is the set, and I will refer to that as the set of epsilon insiders. For what follows, the complementary set, the epsilon outsiders, the complementary set to that will be much more important, but have both concepts in mind. And after that, what we simply do in updating is taking all the ones within the confidence interval of an agent, divide by the number of agents in that confidence interval, and that's it. That's the whole story. Okay, now 3 examples. As usual, here we have time. That is the unit interval with the opinions. And for a very small epsilon, what we get, you see it here. After a while, not very much periods, it gets stable. Lots of clusters survive. They started with 50, but I think it is still 13 or so. If epsilon is bigger, we get here kind of polarization. And for an even larger epsilon, consensus in a very short period. Why? Well, that is not that difficult. No? Here you see an example dynamics. What do we see? Well, at the extremes, the opinions move direction center. Why? At the extremes, opinions are under a one-sided influence. There is no one up there. And therefore, we have a pull direction center. You see it here and there. Here, at the bounds of the profiles, opinions start to condense here and there. The condensed opinion, given the epsilon that we have here, pull downward, pull upwards, opinion in the center. Here in that period, that is period 4, we see no longer than here a vertical line. By vertical lines, I connect vertical dark gray lines. I connect opinions, neighboring opinions, that are not further away than epsilon. So as long as there is a vertical line, we have mutual impact. Whenever we have a split, and that is done here, occurs here, there is no longer any impact of opinions here on opinions above. In both split partial profiles, we get direction 1 opinions in 1 more time step, and we have a polarization. That is what basically happens. We have a shrinking and condensing of opinions in the profile in certain areas. Then the profile splits in parts, do no longer influence each other. Finally, in split sub-profiles, all opinions are within the epsilon reach of everybody else. As a consequence, next period, we have the same opinion in that part of the profile. That's it. Okay, in terms of interpretations, well, opinions, I started with probabilities, but we can think of lots of other things. Whenever we can reduce something into the range of 0 and 1 in a serious way, we could consider that as an example. We could even think of preference intensity under certain conditions, namely intersubjectivity as to comparisons. Moral praiseworthiness, and people have done that, by the way. They interpret the opinion as praiseworthiness or budget shares. All that is possible. I started with the example Delphi study, but think of different contexts of applications. For instance, whenever compromise, for any reason, is motivating people, we could think that that is somehow modeled by the mechanism. The reasons might be uncertainty, respect for others, or pressure, preference for conformity. All that might be context for an application. Everybody knows confirmation bias. If you would ask, and what is it? Well, think of bounded confidence as try to explicate what could be meant by that, and explication in terms of we want to quantify it. How strong is that bias? That is a way to think about that. in more modern world applications terms, you could think of centralized social media in which a central algorithm lets meet people whose positions are not too far away from one another, or decentralized media in which everybody can send a message to everybody else, but the others only take care of the opinions that are close enough. That are applications. So it is not only descriptive, it is also, for instance, normative. In philosophy, social epistemology, you have debate, peer disagreements. All involved debaters consider mutually themselves as reasonable, nevertheless disagreement, what to do. And one position in social epistemology is split the difference, come closer to each other. One could have another view on that, but that is one position. And you could say the model simply explicates what could be meant by the recipe, split the difference. Does that really lead to consensus, or under which conditions? Okay, that is about the model, and thinking about how it works. There are some very trivial insights. If epsilon is 0, it is clear nothing will happen. Everybody will stick to his or her opinion forever. And if epsilon is 1, in the next period, we have consensus, simply the mean of all opinions. That's it. But what is in between? And now the question is, what's about this range in between 0 and 1? When we wrote and published this article in 2002, we did not state that explicitly, but we believed the following. With an increasing confidence level epsilon, the number of final clusters decreases monotonically from plurality, polarization to consensus. The type of analysis that we used then suggested that. And we did not write that, but we believed it. And we didn't write it because we considered it trivial, too obvious to be stated. And secondly, with an increasing confidence level, the width of the final stabilized profile shrinks, and again, monotonically. We didn't write that explicitly. Our statistics and our visualizations suggested that, and we didn't write it down because, again, we thought too trivial to be stated. That were our beliefs. As you guess correctly, that is all completely wrong. The model is deceptively simple, and in an article of two mathematicians, Swedish, Edwin Hedin and Peter Higati, one finds the nice quotation. I like it. The update rule is certainly simple to formulate, though the simplicity is deceptive. And now I want to explain what is indeed the case. And I want to propose a new and other type of approach to analyze the model. And that is a type of analysis in which somehow what we overlooked back then becomes, in a certain sense, unmissable. You can't but realize that it is wrong. And that is another type of analysis. And the analysis starts with a very simple question, and that is, given a star distribution, how many different processes can be generated at all given that start distribution. What is possible at all? I mean, epsilon is taken from the real valued unit interval. Is it an infinity of possibilities? Is it a certain finite number? And if so, which epsilon values are the ones that constitute the epsilons that really matter, make a difference, and then we count them, and maybe that is finite. To discuss from that starting point the problem, I will do that with a very simple example. It is an example with just 5 agents, all of them with different opinions, and that are the 5 opinions. 0.0, 0.18, 36, 68, 1. So they are positioned here, there, 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 and there. We start with 0 equal epsilon equals 1. Nothing will happen, of course. No. That you see. But now the question is, what epsilon will happen? In going through the dynamics, I will always use, by the way, this color map. And that is a color map that colors the upward and downward pull on opinions. Blue is in an upward direction, the shades of red downward direction, and the net pull is basically only this, the distance between opinions in t+1 and t. That distance is the pull on the opinions. And if we now ask ourselves, what will happen? What will happen? And what is the first epsilon that makes a difference for this start opinion? For what do we have to look? We have to look for the smallest distance to others that we have in this start distribution. We have to look for the nearest epsilon outsider that we find anywhere in the profile. Where is it? Well, that is here and there the case. And the distance is easy to determine. It is 0.18. The first epsilon that makes a difference given this start distribution is an epsilon of 0.18. That is what we have seen before. If we run the start distribution or the BC process given the start distribution with the epsilon that was the first one to make a difference, if we do that, we get, can we get that a bit? Thank you very much. Then we get Z dynamics. That is the first epsilon that makes a difference. And now we repeat our type of reflection. For that dynamics here, what is the epsilon, the next bigger epsilon that might make a difference? Well, again, we look for the nearest epsilon outsider. We have 2 here between these 2 and there between them. Okay, we run the dynamics with a newly found epsilon switch, the second epsilon that matters. We took it from that example. Here were the 2 next neighbors, next epsilon outsiders. And if we run that dynamics, we get this one with the consensus. In that dynamics, we again look for the nearest distance to an epsilon outsider. If we do that, we find that nearest distance here. And we can run the dynamics with that. And you immediately realize I use a search algorithm now. And it is a very simple search algorithm I start with my start distribution, set epsilon to 0. Look in that start distribution. I run that distribution. I run that start distribution with that epsilon and look in the whole process that I get for the distance to a nearest epsilon outsider. Once I have found that, I write that in my list, set epsilon to that delta. I know that the largest possible switch that makes a difference is simply, my profile is ordered, the difference between xn minus x1, that is the largest. And as long as I do not get there, I continue, and that way I get my epsilon value, my epsilon switch values. We can do that here. That is the next dynamics. For that, we get then a consensus. That was our last example. That is the new one. We get here our next epsilon. We run the dynamics with that. And now our network falls apart. It falls apart here. Consensus turns into polarization. That occurs here. We look for an epsilon switch that makes a difference. The smallest distance to an outsider is here. And if we run the dynamics with that, we get again technical problem. No. Okay. Should mute the microphone. I could speak to the participant.
No, I'm not. Everybody's muted. I think we are all.
Yeah. Okay. Okay, so we got, I have to repeat the point. The point was we had consensus already, looked for the nearest outsider, got this type of polarization. From here, we get this as the next epsilon switch that matters. And if we run the dynamics with that, we get consensus again. We refuted the intuition of monotonicity. That is our first example for that. Okay, my algorithm works. And if we apply this algorithm on this start distribution, we find exactly 13 epsilon values that matter. And only 13, not more, just 13. Here they are listed. The 13 epsilon switches exhaust completely what is possible in terms of BC processes for that start distribution. And if we go through the cases, then what we see is we get here from consensus to polarization and then back to consensus. Here are the values of the switches. You may be surprised that I use suddenly here fractions, but that has a certain reason. This algorithm does not work with floating point arithmetic. In terms of floating point arithmetic, you will get completely corrupted lists because of minor rounding errors, which let explode the number of switches, which are not there, but are only artifacts of rounding, artifacts of the floating point arithmetic. And therefore, I can go into the details. I paid a high price for learning that floating point arithmetic might cause numerical disasters, which have serious consequences. Okay, I will go back to that later, maybe. What do we get by this approach? What we get by that is, as the confidence level increases, we get a certain number going through all possibilities. We get a certain finite number of switches, and the switches deliver a complete segmentation of the space 0, 0 to 1. We have this right open intervals, and for all epsilons within one of this right open interval, the dynamics is always the same. Almost all epsilon values do not make any difference. Almost all. Only a finite number does. And they are intervals of the type right open. You can get them im Übrigen, you can get them left open as well if you simply change the epsilon condition from not greater than to smaller than. You would get the same list of epsilon values that matter, only the definition of the interval is different. It is then left open. Okay, that is main lesson, and looking at here our 13 possibilities, 3, 4, 5, that is the decisive example of non-monotonicity. I'm not the first, and I want to state that open, to detect this type of non-monotonicity. The first one to find that is Jan Lorentz in his paper Consensus Strikes Back in the Hexagon-Krause model, an article from 2006. That is an excellent article, but what Jan finds there is only the tip of the iceberg of non-monotonicities. He still applies the floating point arithmetic. He detects the problems of that, can't continue his type of analysis because of that. And well, I have an approach how we can cope with all this stuff. But he was the first. Okay. Now we find an example, but we want to know, want to know more. We want to get more general insights, and that I want to present. What I want to present now is an application of this approach to equidistant start profiles. And I want to answer some questions for the whole class. Equidistant start profiles are constant distances between the opinions in the start profile, and there are two interesting or especially interesting equidistant start profiles. That is, first of all, a regular start profile, or what I call a regular. Destroy this device. And the problem is the long cord. The regular start profile includes 0 and 1, and it is always distributing n opinions between 0 and 1 equidistantly. But there is another equidistant start profile which is at least of the same importance, and that is what I call expected value start distribution. in which the opinions are distributed according to this principle. The expected value start distribution realizes deterministically an idealized or repeated runs of an uniform random start distribution. If you again and again have random start distribution, uniform random start distribution, sort the opinions again and again, and look what in the long run is of the rth opinion in the profile, the opinion R. That is what you get. That is, there is the opinion. Of course, as n goes to infinity, that one goes into that direction. It is important because often it is possible to substitute iterated runs based on uniform start distribution by just one run that starts with this deterministic idealization, what in terms of explanation makes it much, much easier to understand what is going on. No statistics involved any longer after that. Okay, that is the reason why to focus on, or why even under empirical perspectives, it is interesting to understand what is going on for equidistant start distributions. Okay, now let's do that. And we can do that. And here you see, first of all, universal results for equidistant start distributions. We now consider equidistant start distributions with 2 to 50 agents. How many switches, how many epsilon values that really matter do we have? These two graphs, blue and red, show you what is going on. Blue is even values, red odd values. And we see how it increases. Probably it is a polynomial increase. I do not know. I could only compute up to 50 because if you do fractional arithmetic and you need additionally integers of arbitrary length, in your calculations, you will get that huge numbers. They are really astronomical. Already for n equals 50, you get denominators that are equivalent to half the estimated numbers of atoms in the universe. That is the order of magnitude. And that has consequences for the computational speed. It gets reduced by compared to floating point arithmetic with similar tasks, gets reduced by 2 orders of magnitude. It is really slow. Something can be done on that, but that is the case. And what you see is, well, okay, red is always higher than blue, meaning the number of switches for odd values of n seems to be, but that is not a proof, seems to be always slightly higher. There is something very general the case. The number of switches does not depend on the equidistance or the size of the equidistance. For all equidistant start distributions, it is the same number. It is simply the same, whatever the distance. It is true, the position of the switches, that is different. But the position of the switches depends upon the size, and you can transform that in a very, very easy way. So if you study, I consider somehow the regular start distribution as the mother of all equidistant star distribution, because it is psychologically easy to understand equidistance 0 and 1 included. At least for my simple mind, it is easier. But we can, I stress the importance of the expected value star distribution. We can get the values, the positional values, by this simple transformation out of our results for the regular star distribution. Therefore, we have it. Okay, number of switches is one thing, but my focus is non-monotonicities. Now they come. Here we look for 2 to 50 equidistance of, and that regards the number of agents. And now we look for switches from consent to polarization. How often do we find in the specific star distribution then switches that destroy a consent and turn it into polarization? And we see, for instance, here for 42, 6 times it happens. 6 times consent destroyed, restored, as epsilon increases for an equidistant star distribution with 42 agents. Okay. It never happens for odd numbers. Well, why? If we have an odd number of agents, we have always one opinion in the center of the opinion space. That opinion will never move, and therefore it is not possible. It is not possible that such star distribution gets ever from consensus to 2 opinions in a polarized matter. But it could happen that in the center we have one, but it could happen that we get from consensus to 3 clusters again for odd values of n. And as we see, it happens. There seems to be a pattern. To find out what is really the case, probably one has to calculate for higher values of n, what I wasn't able to do so far, but will do. But you see already what is going on. Here for odd values, we have even 7 times now for a star distribution. Consent 3 clusters, consent 3 clusters. Or let's look for the more general case, that for 1 epsilon we have a certain number of clusters as the final stable results, and for the next switch more clusters. That includes the cases with a destroyed consensus, but includes other cases as well. And we see that happens all over. Here it is 19 times probably for an n equals 42. Another result, final profile width. One would expect, we thought that final profile width will shrink as epsilon increases. But here are the cases where it does not shrink. And fairly often that happens. And since we know the switches, we simply go through all the switches and check for non-monotonicities of any type we are interested in. And then we find out that is how it is done. Okay, that is number of switches, but we may be interested in positions of clusters that we finally get. And now we can use, to get a better understanding, now we can use another and new type of diagram which demonstrates what is going on by the switches that are involved. And we focus on the case n equals 42. That was the case in which we got 6 times consents destroyed by the next switch. We are interested in what is going on. Where are the clusters that destroy? And in this diagram, you see vertical lines. The vertical lines indicate the positions of the switches. I only look into this area up to 0.3. And in that area, we find a total of 401 of 46 total number of switches. The vertical lines indicate wherever you have this upward triangle, wherever you have that, there is the non-monotonicity in terms of switches. Number of in terms of clusters. The number of cluster is increasing compared to the predecessor switch. Red means a consent falls apart. We have two clusters, or in this orange-yellow triangle, that is the case. A consent destroyed, and we get 3 clusters. Here, downward, black triangles indicate that we have an increase in the final profile width. So triangles indicate the cases of non-monotonicities, and the colors, okay, that is the relative cluster size, and you see the positions. Have in mind, gray circles, that is consent. And we find here in this area, marked by triangles as well, here we find very much the cases of this strange behavior, non-monotonicities again and again. Okay, in that figure, we can't see the details anymore, but having the list of the switches, we can magnify. And here you see what is with this gray background in this diagram. Here now, this section only, and you see better the details, what is going on. I mean, that is very special. N equals 42. One would like to know for every n, basically, what is going on. I have types of diagrams now in which that can be shown. That is the type, but to leave some time for discussion, I go not into the details of this type of diagrams, and I go directly to a next step. And that is meant to underline what I meant in terms of understanding made easy by using equidistant start distribution, which can substitute enormous numbers of random runs. That was what we have seen as the last slide, magnified a certain section of epsilon switches. That we see non-monotonicities all over. We would like to understand why, how comes? Well, okay. Each switch corresponds to a unique single run. And therefore, we can go into the single runs. These are 42 switches that we have in between. That is the start of all the switches in that interval. We see that dynamics. It is stabilized in period 8. And now we go through the 42 switches. You see a movie that what is by far too fast, but I did not find so far the possibility to get the speed under control. Something was changed in this damned Apple app that allows to produce these movies, but it is not a problem at all. You see, we can go through it. I repeat the movie shortly. Okay, you have a feeling And now we go into 2 slides. I have 3 dynamics. The dynamics for consecutive switches. In the first one, we have this, polarization. It is caused because here in that period, the network falls apart. We have here in the center one, here one, and down here one. Under the next switch, what happens is something that happens to this opinion. The trajectory changes to that one. Under the bigger epsilon, this opinion becomes a bridge between the outer cluster and the center. And the same, I mean, I have an equidistant star distribution, it should be completely symmetric. Happens here, the dynamics becomes much, much longer. But by having this bridge between the center and the outer cluster, finally, we get to consensus. And now I go to the next switch, a bigger epsilon. And that bigger epsilon destroys the consent again. That we had and that we get. And it is again this former bridge which is destroyed under the bigger switch, the bigger epsilon value. And we have this structure with 3 opinions, finally. Okay, I come to an end, a concluding remark. Well, that were our intuitions, and there are more intuitions. And probably all readers had this intuition as well, except for Jan. Jan was a PhD student of Ulrich Krause and me, got his dissertation in Bremen. He found out that it is not true, but he did not deliver compact and all-compassing analysis of the problem. The complete story is, well, yes, of course. Finally, as epsilon increases, we will always get consensus. But the transition to that is not smooth. It is really wild, a wild, non-monotonic process. And with that, I want to close. Many thanks.
Right, thank you very much. So this is open for questions or comments. Anybody has any?
Thanks for the talk. Question: is your intuition or what you believe everyone else is still correct in the limit of n going to infinity?
N going to infinity. Well, in that, no, I do not dare to give an answer. I got doubts about that, but I'm not sure, and I have not real opinions about that. Or I ask you the question, N going to infinity with regard to an equidistant star distribution.
Yeah, that's right. How I always thought about all of it.
I know.
Infinite number of agents with flat distribution between 0 and 1.
Yeah. I mean, in this article that I cited, Jan had written, Jan discussed a conjecture that I had written in a footnote about the case N going to infinity. And I had written in that footnote, I guess if N goes for any given epsilon, if N goes to infinity, it will always lead to consensus. That was my conjecture. There is always a point where there are that many that never ever there is falling apart of the network. And as long as there is a connected network, it will get to consensus, that is for sure. And Jan, writing that article, coming up with simulations, argued finally that probably my conjecture is wrong. Probably, but he could not deliver a proof. I'm only now, I really read in detail, I'm sorry for that, Jan's article, and got into doubt. I do not know. I have to think it through again, and to try out, by the way, to try out. But and your intuition is?
Is that your intuition was correct? And going to
Please write a mail to Jan. Well, no, I'm getting doubts. I do not know. Back then I was sure, but that is gone, as a lot of things I was sure about.
Any other questions or comments? No.
Yeah, we should actually use them. Yeah, I ask, how typical is this behavior? How much does it depend on the fact that the initial condition is equidistant between the opinions? You start with an equally distant, right? You start with a random initial condition.
Yeah.
And then how many cases would you get that monotonic behavior? Will the fraction go to zero, or will be significant fraction?
I mean, in normal life, equidistant star distributions are not typical. But they are a nice case to try to understand what is going on if n increases. To get a starting feeling, and then we can go into more realistic types of distribution. That would be the first part of my answer. But I would stress, think about the value of an expected value star distribution. Well, in an expected value star distribution, you deterministically idealize the position of the opinions of repeated random star distributions. If I have this expected value star distribution, I can try to understand what is going on, changing the epsilon values, or now that is how I have done it in the past. I have written an article, it is about radicalization. A radical signal is working on an opinion process, and in that analysis, Ulrich Krause and me, we always used this expected value star distribution that substituted iterated random runs. That allowed then to somehow calculate a phase diagram, a physicist would say. We called it a radicalization landscape, which shows the effects of the strength and position of the signal. And then lots of effects were visible one would like to understand. And in order to understand, because of our approach with just one and the same star distribution for all our runs, we could really understand certain mechanisms that produced a radicalization landscape, a phase diagram, which very strange behavior indicated by that. Okay, if one does that, there is a danger. The danger is that we overlook effects that are due to the fluctuations in the densities of the opinions if I do not equidistant star distribution. Because of that, to hedge against such effects, we later, but only later, run the same landscape with random star distributions. The effect was that we found the same pattern, but it was blurred. It was, of course, blurred by the random star distributions that we used. But what I would say is, nevertheless, that is an interesting approach, because I get a feeling for mechanisms it is that easy to understand what is going on, why? Because you can go into the single runs and understand there. And then you have to hedge against what you overlook by the random experiments and real random experiments. But if you see that only the bounds of certain patterns are blurred, then I feel on safe ground. Then I feel on safe ground for my explanations. I have started, I mean, that was strange. Why did I start with expected value start distributions? That was simply because my computers were not good enough. The number of runs that I had to do, I had not the time or not the computers that were fast enough. And therefore, I went to statisticians in Bayreuth and asked them what to do. It must be possible to idealize any type of random start distribution, and let's start with uniform. And then they told me, well, that is the simple formula. And it was equidistant. For if you do the same approach for a normal distribution, it is not equidistant, of course. But for uniform random, it is. So the background was computational problems. And then, okay, that idea to use that.
Thank you. Thank you. I thought it was very interesting, the topic, and actually quite relevant, because I was thinking, for example, now there's a lot of study of interacting AIs, so artificial intelligence interacting with each other to solve collectively a problem. And it's actually very nice to see that you can have a complex landscape of consensus in that space. But actually, when I'm thinking also about maybe consensus in the case of an artificial intelligence or in a general case, I'm actually thinking about maybe using, instead of a variable, real variable between 0 and 1, is there anyone who has studied this in higher dimensions? Like, for example, let's say you can have, a vector of opinions, and because then you can like have a rock, paper, scissors kind of, circle of.
The first part of the answer is Ulrich Krause has written a book on this type of dynamics that includes higher dimensions as well. Lots of people have extended the bounded confidence model and done work on higher dimensions. There's one article of Ulrich Krause and me on that. You can get it. Well, okay. So it was done. Personally, I think, and I'm doing that now, but it takes a bit of time, this approach, of course, can be applied to higher dimensional opinion spaces as well. And I can look for the switches. I can look for the switches. But there is a serious numerical problem then. If we go into higher dimensions, we have to define what we mean by neighborhood. What is the follow-up solution for my epsilon? You could say, well, we have to have an epsilon distance not greater than epsilon in all dimensions. That is a conjunction. Or you might say the sum of the distance not greater than epsilon. If it is like that, it is easy. But, and that is very suggestive, if we say we turn to a Euclidean distance in the two-dimensional case or something analogous in higher dimensions, then it becomes a problem in 2 dimensions. Square roots become involved. As long as I do computations in terms of addition, subtraction, division, and do that based on fractional numbers, I still am in the space of fractional numbers. But if we use Euclidean distance, we leave the space of fractional numbers. We have irrational numbers involved. And I do not know at the moment how to stick to exact arithmetic. if I get square roots. And the square roots, I think by them, my absolute exactness gets destroyed because irrational numbers and then arbitrary length of integers, that does not help. It is not sufficient, simply not sufficient. And that is the problem that I have. But what I started is a project with this more trivial types of neighborhoods, which are then always squares of a certain type and with a certain direction, either conjunction condition in all dimensions not greater than, or this additional version of neighbor sum not greater than. Then it works. No? And I think that this type of analysis would show that in a certain sense you can learn, as long as equidistance is the condition, you can learn everything about the higher dimensions by simply studying the one-dimensional case, because by easy transformations you can go through all dimensions. That is what I guess, and I think I even have for some things a proof of that. I'm not completely sure about whether it is real, the proof. I have to go through it again, but there's space for research with the higher dimensions.
I also wanted to ask about the, if you do not have a bound on your opinion variable, because your opinion here goes from 0 to 1, and that seems to be what triggers the asymmetry in the bounds and, you know, creates the polarization in the first place. But if if you don't have any bounds and you have an equidistant distribution, then
yeah, I mean, you could think of it is not a upper bound, and we have a circle of opinions, one-dimensional case, but it is a circle. I always thought, what is next application for that? And I found only one, by the way. There is one, I think, and that is if you discuss about directions, in which direction to go, then you would have such a case. But are there more? I mean, I find it interesting. One, even if there is no application, I would say that is an interesting case to be studied. One application is there, but are there more? I would like to hear about other examples. Is that an announcement? No.
Yeah, I think actually we have to wrap up, because it's, I think, more than an hour and the coffee is waiting, and we don't want it to get cold. If it's hot, I assume. So thank you again for this very nice talk.
I thank you.
And I should say Rainer is around today for the rest of the afternoon and also tomorrow afternoon. So if anybody would like to talk to him, let me know and I can arrange it. Okay. Okay. Thank you everybody for coming.
I'm sorry for trying to destroy the microphone. But that is